Welcome to part 3 of chapter 4 on directed graphs. In this part we focus on rooted trees. Let us define what a rooted tree is. Let G denote a directed acyclic graph. We say that G is a rooted tree if it satisfies two conditions. There is a single sink in G, and for every vertex in V that is not a sink, the out degree equals 1. The single sink in a rooted tree is called the root, and we denote the root of G by R of G. So let's see some examples of directed acyclic graphs, some of which are rooted trees and some of them are not. In the first example, on the left, we have a directed acyclic graph, and we have this node whose out degree is 2. The fact that its out degree is 2 means that this graph cannot be a rooted tree. Moreover, this graph has two sinks, this one and this one. So that's the second reason why this graph is not a rooted tree. Let's look at the second graph. In the second graph, which is also a directed acyclic graph, we have a node whose out degree is 2. Therefore, this graph is not a rooted tree. The third graph that we see, every node has an out degree 1, except for one node, which I call here the root, which is a sink. So there's a single sink, and all other nodes have out degree 1. Therefore, this graph is a rooted tree. We want to prove the following theorem about rooted trees. There is always a unique path from every vertex to the root. This is an important proof, and I will present two proofs for this theorem. So we want to prove that if G is a rooted tree, then for every vertex there exists a unique path from the vertex V to the root. The first proof is by induction on the size of V, on the number of vertices. The base case, when there is a single vertex, is trivial. The induction hypothesis states that the theorem holds if the number of vertices is n. In the induction step, we want to prove the theorem for the case that the number of vertices is n plus 1. Now, G is a directed acyclic graph. We have proved already that in every directed acyclic graph, you have at least one source. So there exists a source in G. Denote the source by V. Consider the directed graph G prime, defined over the set of vertices V prime and set of edges E prime, where V prime is the set V minus the set that contains V. Namely, V prime consists of all the vertices except V, where V is the source that we found. E prime is the set of all edges except for the edge which emanates from V. Recall that V is a source. It's not a DAG with a single node. Therefore, the out degree of V has to be 1. It cannot be both the source and the sink. And there's only one edge which is incident to V, and we omit this edge in order to obtain E prime. Now I claim that G prime is a rooted tree. Why is this true? Well, in fact, all I need to show is that the out degrees of every vertex U in V prime is the same as the out degree of that vertex in the graph G, in the original graph. And then, if I prove that, then I will get that there is exactly one sink in G prime, and all other vertices have out degree 1. Indeed, the out degree of every vertex is unchanged by removing the sink V and the edge that emanates from it. Now, the graph G prime has one vertex less than the graph G. Therefore, the cardinality of V prime is n, because the cardinality of V was n plus 1. So we can apply the induction hypothesis to G prime. What does the induction hypothesis tell us? It tells us that for every vertex U in V prime, there exists a unique path from U to the root. So we're left only with dealing with the node V. This is the source that we found in G. What can we say about V? We can say its out degree is 1, therefore there exists a unique vertex U such that there is an edge from V to U. So here's V, there's only one edge that emanates from V and enters the node U, and U is in V prime. So we have already shown by the induction hypothesis that there is a unique path from U to the root. Therefore, we found a unique path from V to the root, and that completes the proof. The second proof is divided into two parts. In the first part, we show that there exists a path to the root. In the second part, we show that there exists a unique path to the root, that there cannot be two distinct paths to the root. How do we show the existence of a path to the root? Pick an arbitrary vertex V, and we build the path to the root recursively as follows. Define V0 simply to be V, and now we have the stopping condition. If we reach the node Vi that is a sink, then we stop, and the reduction step. If Vi is not a sink, then there exists a node U such that there is an edge from Vi to U, and now we define Vi plus 1 simply to be the node U. So having defined V0, V1, V2 up to Vi, we define Vi plus 1 simply by extending the path by a single edge. This is the edge that emanates from the last node we find. And once we reach a sink, we stop. Now, every path in the directed acyclic graph cannot be too long. We already proved that the length of the path is bounded by the number of vertices minus 1. Hence, this algorithm for constructing the path, or this recursive definition, must terminate. Once it terminates, we have reached a sink, but the sink is unique because it's a rooted tree. And this sink is indeed the root. So the path reaches the root, and that completes the existence of the path from V to the root. Now we need to prove uniqueness. Suppose, for the sake of the contradiction, that there exist two paths from V to the root. So one path goes from V and reaches the root, and the other path goes from V and reaches the root. Now, these paths are different. Therefore, at some point they must diverge. Consider the first node U in which the two paths from V to the root diverge. Now, one path exits U through one edge, and the other path exits U through another edge. That means that the out degree of U is at least 2, and that contradicts our assumption that G is a rooted tree. I want to discuss now the composition and decomposition of rooted trees. Let's start with decomposition. Suppose I have a rooted tree, and the root of this tree is R. Assume that the in-degree of R is 2. It could be any number, but it's easier to depict this situation using an in-degree of 2. Let R1 and R2 denote the vertices of the rooted tree from which there are edges to R. Now, define V1 to be the set of all vertices such that the path from V to the root R traverses R1. So all the vertices that in order to reach R have to go through R1. Similarly, define V2. All the vertices whose path to R traverses R2. Now, we have a partitioning of the set of nodes not including the root into two sets, V1 and V2. And we let E1 denote all the edges between the vertices of V1, and V2 all the edges between the vertices of V2. And we have two more edges, the one from the root R1 to R, and the one from the root R2 to R. Why do I say root? Well, in G1, which consists of the vertices V1 and E1, the out degree of R1 is 0. And the same holds for the out degree of R2. All the other nodes in G1 have an out degree of 1 because the edge that emanates from them is preserved, and the same holds for G2. Therefore, G1 is a rooted tree, and G2 is a rooted tree, and G1 is rooted in R1, and G2 is rooted in R2. To summarize, our decomposition takes a rooted tree and decomposes it into subtrees. Each such subtree is rooted at a node from which we have an edge to the original root of our rooted tree. What is composition? Composition is the situation in which we start with G1 and G2, each of which is a rooted tree. G1 is rooted in R1, and G2 is rooted in R2. And now what we do is we introduce a new node, and we connect R1 with a new fresh edge to R, and R2 with an edge to R. And now we get a new DAG, a bigger DAG, which consists of G1, G2, and the edges from R1 to R and from R2 to R. That would be composition. We use the following terminology when we talk about rooted trees. When we do the decomposition and we look at these subtrees, GI, whose roots are connected to the original root of the graph, we call each such GI the tree hanging from the root. So, in the previous example, this G1 is one of the trees which is hanging from the root. A leaf is simply a source node in a rooted tree. An interior vertex is a vertex that is not a leaf. So the root, if it's not a leaf, is an interior vertex. We say that V is a parent of U if there's an edge from U to V. So in the previous example, R is a parent of R1 and also a parent of R2. Typically, in this course, the degree of vertices in rooted trees will be 2, but this is, not always the case, just the typical case. I want to end this chapter with a discussion of 2 applications of rooted trees. Okay? And in this discussion, I want to emphasize, and when we talk about the rooted trees that hang from R, they are often ordered. We have the first rooted tree and the second rooted tree. Why is this the case? This is an important thing in trees which are called parse trees. So let me explain what a parse tree is. Consider the following expression, A divided by B plus C. We can represent this expression using a rooted tree, the leaves of which are A, B, and C. And now since we add B and C, we connect B and C via directed edges to a node which is labeled plus. We divide A by the sum B plus C. So we connect A to the node labeled by division, and we connect the plus with an edge, again, connected to the division. This is called the parse tree of the expression A divided by B plus C. Now, parse trees are computed or constructed by compilers when they need to write short programs that evaluate such expressions. And once they have a parse tree, they perform topological sorting over the parse tree in order to perform the sub-operations in order to evaluate the expression. Another example is in the field of circuits. We will use rooted trees in order to model special types of circuits which are called combinational circuits. So consider the Boolean formula x and y or z. We can build a parse tree for this Boolean formula as follows. The leaves are x, y, and z. We connect x and y to a node labeled and we connect and to the node labeled or, and the z as well to the same node labeled or. And this would be the parse tree of the Boolean formula x and y or z. Thank you.